understandable as far as your calculations for lab. We ready? We ready? Sorry, didn't have to do that. Don't have to do that. As far as lab itself, we know we do the physical properties of water. We all have fun watching ice melt. No, I know. But your calculations, and don't wait until like the morning of lab next week to do them. You might need a little extra time or help with some of those. If you do it early, you can ask for help. We know we have a quiz on Friday. Hopefully you saw the bullet list go up yesterday. So there are two writing balanced chemical equations, one for an enthalpy of formation, one for an enthalpy of solution. Also, you're going to be using a reaction with a given enthalpy to do a calculation. Make sure to review the rules for enthalpy. I even gave you the page number and lecture activity question number. It was a table with the rules. So maybe review number 11, page 608, 208 of the lecture activity book for that particular set of questions. And then you'll be calculating the enthalpy of a reaction using enthalpies of formation. The enthalpies of formation will be given with the exception of elements in their standard states. What's the value then? 0. Got to know that one. So you probably saw it go up yesterday. Were there any questions about it? Exam 3, about 2 weeks from now, on the 20th, 5:30 p.m., 60 minutes left on 162. I'm rather confident now that we'll be going through the end of periodic trend, which I forgot to type it. I think it's section 8.5, I believe. I will look at that again. I'll make sure to type it up for Friday's reminders there. We'll also be opening up next week's module on Friday, and then we'll have your exam 3 review information. I did add some new little exam 3 questions and lecture activity questions to go with the topic we're going to talk about today, which is quantum numbers. Are there any questions? I have one more announcement. One of your fellow students is trying to organize an exam review. So this is not me, this is one of your fellow classmates. They're trying to organize an exam review. And if you're interested, the person's trying to get a count so they know what size room to reserve. But the person's email address is there. For some reason you don't catch that, you can always send me an email. I can send it on to you. Oh, I forgot to take a picture of that or write it down. What was that email address? They are planning on Friday the 14th from noon to 1:30 p.m. Location still yet to be determined, but they've already enlisted a volunteer TA to basically lead the review. So they've done a lot of work on their own in advance. So if we can get some people to attend, that would be well worth the work then. So I'm just going to leave it up for another minute or two in case anybody wants to snap a picture of the email address. Otherwise, I can also share that with you. Please just send me an email. Any questions? Good? Okay. We will be starting chapter 7 right near the end of the video. Again, I'm still pausing a little bit in case anybody wants that information. Just so you know, we will be starting number 19, page 228. The beginning part of your lecture activity page are covered in that video. I might put that up again at the end, just in case. So remember, the video did cover almost half the chapter. It is lightly tested in that, if you watched the videos, you saw this slide, I think, both at the beginning and the end of the video. You'll be tested on the conceptual aspects of the material. You will not need to be able to calculate using the Rydberg equation or any of the equations in that video, not even on your final exam, and depending on your major, you may never use them, which is why I do this. There are some little problems, the ones that were assigned already, for which you will need to calculate using equations in these sections, but of course, it's homework. You can get help, you can ask questions. Are there any questions about what we expected of you? Yes? Conceptual, not calculation. For example, what happens to an electron when you give it energy? It gets excited and it moves up to a level further from the nucleus, right? Then it relaxes down to the ground state, things like that. So you should know what excited my words just left my brain. Excited, relaxation, ground state, things like that. The main ideas of Bohr's orbits in his model, but not having to calculate. This is the exam. Okay, we already put up the goals for the quiz. There's nothing on chapter 7 there yet. Okay? All right. And by saying yet, I didn't mean to imply model electrons as particles and waves. So an electron can be thought of as both a particle and it can be thought of as a wave. Just like a photon for light can be thought of as the photon itself, the particle, or the light wave. What does this mean for the model of the atom? Right now we use probability theory. Whenever wave mechanics are involved, we have probability involved. So the modern model is a probability theory model. Which means we really don't know where the electrons are. We'll often say the highest probability of finding the electron would be this particular volume of space. Is it accurate, therefore, to dot electrons in an atomic model? Not really. By that we mean, if I wanted to draw a Bohr model of hydrogen, there's my proton for the +1 nuclear charge, and I can say I'll put an electron there. It's not really accurate to do that because we don't actually know where the electron is. However, we still do it because it helps us understand. Okay? So it helps our understanding, kind of like a redox. The oxidation reduction don't happen separately, but we write it like that because it helps us understand. How do we account for the atom not collapsing onto itself? This actually got put in a couple of years ago because it was a very common student question, such a common student question. I went to the author saying, please put that in. Because students are like, well, if electrons are negative and the nucleus is positive, why don't the electrons just stick to the nucleus? Yes, we have electrostatic attraction between our opposite charges, between our electron and our nucleus. However, the motion of the electron itself is what keeps it from not collapsing onto the nucleus, meaning the kinetic energy from that motion actually cancels out the electrostatic attraction. You can think of it as having a bucket and a string, and you put the bucket of water and you spin it just right, you can spin it over your head without getting wet. So you have forces counteracting each other, so that's why the electron, or the atom, doesn't collapse onto itself. C gets more into this probability theory idea, Heisenberg's uncertainty principle. I will say it, but then I'll write it without talking because then I might mess it up. We cannot know both the position and the speed of the electron with any perfect accuracy. Okay? Any object, again, with wave properties is affected by this, which is why it's all probability theory. As usually his name I messed up. And know a little bit about each. Any questions on number 19? It does jump around a little bit. In 1926, Schrödinger wrote an equation that describes both the particle and the wave nature of the electron, meaning he put together the ideas of thinking of electrons as having mass, being particles, versus behaving like waves. And this is called a wave function. So number 20, what is a wave function? What does it describe? It describes the energy of an electron with a given wave function. So every electron has a wave function that helps describe its energy. And more importantly for us, it also describes the probability of finding the electron in a particular volume of space. Schrödinger's equation is kind of like Bohr's model in that it can only be solved exactly for the hydrogen atom. Bohr's model only worked perfectly for the hydrogen atom. Meaning we must approximate the solution to the wave function for multi-electron systems. And that's what all will have to do with it. If you're going to be a chem major, you'll have a whole semester of playing around with wave functions. Any questions? The reason why we have to even bring up a wave function is because of our topic today, quantum numbers. So on the top of the next page, you're asked, what are quantum numbers and what do they tell us? Again, every electron has a wave function, therefore every electron has these solutions to that wave function. They describe the distribution of electron density, meaning 3 of them act as a GPS location device and help us narrow down the highest, where is the highest probability of finding this electron in what volume of space. And then the last one tells us something about how it behaves. Good? Number 22 really seems misplaced for me in my mind. It's like, why are we talking about it now? Bless you. We're going to talk more about it later, but I don't like skipping around too much unless I have to. An atomic orbital is actually a computer-generated image of the wave function for an electron in an atom. So this particular plot of this particular electron's wave function is giving us a spherical shape. Does anybody remember what the type of orbital is shaped like a sphere? The S. So this particular electron is the highest probability of being in an S orbital. We're going to go through all the different shapes of the orbitals, but it is different than an orbit in that now it's 3 dimensions, okay? Bohr's theory would have just been the circle, the orbit going around the nucleus, whereas the modern model, now we realize that the electrons are not restricted to a particular 2-dimensional plane, but they can move in all 3 dimensions, and they're not fixed at a certain distance from the nucleus. Note, it gets darker green as you get towards the middle. The more green, the higher probability of finding the electron. It should make sense. We have a higher probability of finding the electron near the positive nucleus. However, there's still a probability of finding electrons, the green haze, further away from the nucleus. So all an atomic orbital is a computer-generated plot of a wave function for an electron. That is technically the end of section 7.5. Any questions? I did put the bottom of the page on the electroactivity list along with the next page. I'm going to flip my slides, not going to seem like much. All we did is add something to the title. Again, in case there was a break between finishing 7.5 and the beginning of 7.6, we have this review note, although we just talked about it. What are atomic orbitals? Again, they're coming from our wave function. How do they differ from atomic orbits? They're 3-dimensional, whereas the orbits were 2-dimensional. What is a boundary surface diagram? It really is that circle. Before I use the circle to illustrate Bohr's orbit, but we can also put that circle around this plot of the wave function, and a boundary surface diagram is basically, when you look at an orbit in a textbook, it doesn't look fuzzy like that, right? You see what seems to be a surface. That is the boundary surface, and we're bounding in the highest probability of finding the electron. Generally, it is used to encase 90% probability, meaning when you look at an orbital in a picture that is a boundary surface, it's encasing the highest probability of finding the electron, but that means there's still 10% probability of finding it outside. Notice we're not encasing all of the green. There is still some haze outside the circle. It's a little important when we look at our coming images. Any questions? You can see in number 3, we are coming into our quantum numbers. So for each of our quantum numbers, remember that our solutions to the wave function, we're going to consider the symbol for the quantum number. We're going to think about the rule for which actual values are allowed. Then we're going to think about, does the quantum number tell us anything about the atomic orbital or the electrons within the atomic orbitals? And then what differentiates different energies of atomic orbitals within an atom? So we can see we have our first table on page, near the bottom of page 232. And I will actually, since we'll be clicking, I'll kind of keep a running total of some important information about each one. So our first one is the principal quantum number. Notice we recycled Bohr's N. He was on the right track, so he's going to throw his whole theory away. He labeled his orbits away from the nucleus with N values, right? N equals 1 was closest, 2 further away, 3 further away yet. So, following in that trend, the rule for which values of N are allowed, we start at 1, and we increase by whole numbers. So I'll say rule, N equals 1, 2, 3, etc. No negatives, no decimals. How atomic orbitals vary with varying values of N? Well, think about Bohr's orbits. Closest one was a small circle, closest to the nucleus. Well, if you just make that into a three-dimensional sphere, it's a small ball. As you went out, the circle got bigger, therefore the ball would get bigger. As the value n increases, we're getting further from the nucleus. Therefore, the volume encased is also increasing. N increases, size increases. Bless you. How the energy of the orbitals vary with different values of n, if you really paid close attention to stuff with that Rydberg equation, you would have seen as the n value for Bohr's idea increased, the energy increased. The same thing is true here. So if we have an electron in a higher energy level than one in a lower energy level, that electron would have a higher energy. N tells us our energy level. And I have some data just to help you think about the size increasing. So for energy level 1, we have a smaller volume of space encased. Energy level 2, it's bigger, a bigger ball. Energy level 3, it's even larger. Are there any questions? Our next one on, let me actually hold my page, I know where we're at. On page 233 is the secondary quantum number, or also called the angular momentum quantum number. The symbol is L. Notice what's also up in the header of your table, parentheses, sublevels. When we put N and L together, we get sublevels like 1s and 2s and 3s and things like that. So L will end up telling N and L together will tell us sublevels. Let's look at the rule. The rule for which values of L are allowed. Note, we have to know N. We always start at 0, the min, and the maximum is N minus 1, meaning 1 less than your N value. So there's a range of possible values. So we start at 0, and we, I want to write it the same, increase by whole numbers until we get to N minus 1. For example, if your N value is 3, you have 0, 1, and 2 available that are possible. How our orbitals vary with different values of L, the shape changes. We go from balls to balloons that look like they're twisted to all kinds of weird things. So the L also tells us which type of orbital. So I'm going to say this, but I'm also going to say and which type of orbital. How the energy of the atomic orbitals change with varying values of L. If we're in the same energy level, same N value, the lower the value of L, the lower energy. And notice I put a translation underneath in parentheses. Yes?
What does that say after N, L on the bottom before N?
Right here? On here or on the slide?
Where were you pointing?
So this N with L together will tell us the sublevel. And it also tells us which type of orbital, like S, P, D, or F. I put the translation there. We use the letters S, P, D, and F, while the output of the wave function is a number. So if you have an L of 0, that tells you an S orbital. You would have an L of 1, that tells you a P orbital. L of 2 tells you a D orbital, and L of 3 tells you F. We're actually going to look at these orbitals. You can see you have a table in part E. Any other questions before we do that? So, again, for the number 0, that would be our letter S, and S orbitals are spheres. So the shape, I wrote spherical. You could draw a ball if you want. Whatever helps you remember the image. Note, you're also asked about a node. A node is a point of 0 probability of finding the electron. If you have a basketball full with atmospheric air. Use the pump to fill it. Do you think there's any place inside that basketball where there's a 0 probability of finding a gas particle? No, they're all over the place, right? The same goes with this s orbital. There's no point in that boundary surface diagram with a twist or something like that that's telling you there cannot be an electron there. Gas particles can be anywhere inside the basketball, the electrons can be anywhere inside the s orbital. The node equals the value of L. So the nodes for our s orbitals is 0. Any questions before we go on to P? Remember, a number of 1 tells you a p orbital. Many years ago when I taught Chem 100, I had a student say, they look like peanuts to me. And the peanut reminds you of the pea. Peanuts often have 2 lobes. So if you want to call it peanut, that's perfectly fine. And actually my COVID videos have the planner's peanut over one of them. Try to get students to watch. The shape is however you described it. I like to use the word peanut. That student, I still remember that student. There is 1 node. Think of taking a balloon filled with air, not overly filled. You're a clown, you're making an animal, a balloon animal, and you twist it. You would assume if that twist is tight, there's no particles of gas at the twist. Where the 2 lobes join is kind of like the twist of the balloon. There is a point of 0 probability in that boundary surface diagram of finding an electron. I think it's easier to think about balloons or basketballs. You twist a balloon, you're assuming there's no gas particles at the twist. That would be your node. Any questions? Before we go on to the next one?
I'm just trying to make sure I'm filling out the chart correctly. I just want to know if like the red line of the chart was
So that's what I have. You know, I don't often like to share what I have because I want you guys to think on your own. But if you're like, I don't know how I'm supposed to fill this out, then please ask. It's perfectly fine. I know sometimes we fill out tables on paper, other times we don't. This one I like to leave it a little bit more free for the student to fill it out however you wish. Anybody else? Okay. So our next type of orbital is D, and an L value, meaning number 2 for your 3rd row, goes with the letter D for your 3rd row. And I'm the same student, way back when, called them daisies, and for many years I got people drawing little stems at the bottom of one when I put it on a quiz or exam, which is perfectly okay. Daisy starts with a D. And the vast majority of them kind of look like flowers if you put a stem on them. There's one that's an outlier. Don't worry about the one that doesn't look like the others. I don't know, he doesn't have friends, I guess. You will have to, at some point, either a quiz or exam 3, be able to identify an S, a P, or a D from an image. I will never use the one that doesn't look like the others. Okay? Because it doesn't look like a daisy either. A mutated daisy? We still put a stem on it, I guess. So I literally would use the word daisy. Yes?
What does that ring represent?
It's part of the boundary surface diagram, meaning within the ring there is a probability of finding an electron. It's separate, yes. It's kind of funky. Meaning, if you want to think about nodes, don't think about that one, although you can see there is an area where there's no boundary surface diagram, and there's a twist. Think about one of the others. Think about taking 2 balloons. You twist one, you twist the other, and you lay them on top. So you've got 2 twists. You have 2 points of 0 probability of finding the electron. These are just, remember, these are these computer-generated outputs for wave functions. For the 4th one, number 3 for your 4th row goes along with the letter F for F orbitals. Our textbook author doesn't even include images of them. So years ago, I found the best images I could, did cite them. I use the word funky because that student used the word funky too, but I really like the word funky because you can see some patterns. The 2 on the outside look alike, the next next two in look alike, the next two in look alike, the one in the middle almost looks like that D. You will not have to identify an F orbital for this class from image. They're funky. The letter for L is 3. That means there are 3 nodes, and it's really hard to see them. The easiest way to see them would be take to the outer ones, or the 2 that are right next to the middle one. The ones with 6 lobes, and think about twisting 3 balloons. You have 3 twists, therefore you have 3 nodes. And now that I made you fill out the column for nodes, I'll tell you, I could never ask a student for the number of nodes on a quiz or exam. So I know it's hard to look at them and see that. For S and P, not so hard. For D and F, a lot harder. So I've never asked a student how many nodes are in a certain type of orbital. I also know your final exam people don't ask either. Okay? I never leave something out that I know will be tested. MCAS I've seen doesn't ask either. DATS doesn't ask either. The farm people doesn't ask either. Are there any questions before we complete the table in F to see how our sublevels come to life? So this is that table. I did put the rule again at the bottom of the slide. I have to show my page. So we're going to start with an n value of 1. So under my headers, I have n, I have L, and then I have NL. And I'm also going to put our code over here, meaning the L number and the letter. Remember, for L of 0, that's S, 1 is P, 2 is D, and 3 is F, although you do have the table right above on your page if you fill it out. So if we have an L value of 1, remembering our rule, we start at 0, we go to n minus 1 as the max. Well, if n is 1, 1 minus 1 is 0, meaning we only have 1 orbital available, or 1 L value available, 0. Which means when we translate, 0 means S, this is 1s with a sublevel. When you took your prep course, you might have struggled a little bit remembering what kinds of orbitals are in which energy levels. Well, it all comes down to the quantum numbers. We only have 1 type of orbital available in the first energy level. And it's an s orbital, meaning there's only 1 sublevel in the first energy level, 1s. If we go on to n equals 2, we always start with 0, but now we can go to 2 minus 1, meaning we can go to 1. Which means there are 2 types of orbitals available in the second energy level, and that translates to sublevels of 2s and 2p. You might have also struggled with why aren't there d's there? It comes down to quantum numbers. For our n of 3, we would have 0, 1, and 2 available. So we have to stop 1 less than the n value, which means we have 3 types of orbitals, which translates to 3s, 3p, and 3d. It's not until our energy level 4 that we have f orbitals available, because then we can have an L value of 3. For n of 4, we get 0, 1, 2, and 3 possible for our L values, meaning 4s, 4p, 4d, and 4f. Any questions at this point? When we get to the n value of 5, we get into more theoretical areas. If we have an n value of 5, technically for our L values, we can have 0, 1, 2, 3, and 4. But we don't have an L value of 4 over here. There's technically, in the theory, G orbitals. But none of the known elements utilize them, meaning none of the electrons in the ground state in the known elements have a probability of being in a G orbital. Therefore, we don't usually teach that until you get to higher level things. But I've had students in the past question that 4. I'm going to, from this point forward, for this row and the next row, only include what the known elements are actually utilizing. Meaning, in an n of 5, we can have 5s, 5p, 5d, and 5f. We actually have elements that have electrons in the 5f sublevel, but none of them use the 5d. So that's totally theoretical. I really wish the author would have stopped with 4 rows, and then I wouldn't have to do this every semester, which is fine. If we have an n of 6, things get even more hairy. We technically can have 0, 1, 2, 3, 4, and 5. None of the known elements use sublevels that include a G or an H orbital. So therefore, for the known elements, we have 6s, 6p, 6d, technically 6f, but we're still looking for them. Meaning, no known elements. Oops. But we're discovering elements every day. So I like to include that one because it still is using stuff from our table. Any questions? Sorry to push it beyond, but that's what students have taught me in the past. It's confusing if I don't include that little talk. Yes?
Could there also be a 6G?
Technically, yes. I crossed out 2 numbers here. I went to this because it goes with our 3 and it shows up here. You know, but I tested some semesters I don't mention this stuff at all. The other semesters I do, and I think the confusion is kind of equal weighted, so I figure more information is better than less. Okay? You won't have to worry about the theoretical things, but you never know. We might have enough elements that use them one day that I might have to start teaching it. We're always finding new elements. Anybody else? This table is just to illustrate where in the past you've learned about sublevels, 1s and 2s and 2p and 3s, where they come from. They come from the quantum numbers. Everything you know about electron configurations comes from the quantum numbers. Any other questions before we continue? On the next page, 234, we still have 2 more quantum numbers to go through. I know I kind of ran out a little bit of room on this other page, but I got a little still at the bottom, so we'll see if we can slide them in. We have, for the top table on page 234, the magnetic quantum number. The symbol is M sub L. As far as the rule for which values of M sub L are allowed, we need to know L. Remember, to find L, you need to know N. So N, L, and M sub L are all interconnected. We go from a minimum of negative, the value of L, through 0 by whole numbers to the positive of the value of L. I forgot to write the word rule over here. There we go. So M sub L goes from negative L through 0 to positive L, meaning you definitely can have more than one value available. How do the atomic orbitals vary with varying values of M sub L? The orientation changes, meaning, on the student view, it tells you the number of orbitals. In the past, you had to memorize, there's 1s and 3p, right, and 5d and 7f. It comes from the value of M sub L, or actually the number of M sub L values that are available. So underneath, I'm going to say, tells you how many orbitals. In a sublevel, or in the sublevel. In terms of people who actually do this for a living, it also tells us which orbital has the highest probability of finding the electron. I'll say it may, can't say it is, may, which orbital may contain the electron. How the energy of the atomic orbitals vary with varying values of M sub L. We use the word degenerate. I like to use the word degenerate also in 102 because it kind of shows students that just because you know one may bad meaning word doesn't mean it always means something bad. Just like evolution or evolve. Evolve can also mean give off heat. Well, degenerate can also mean same energy. Meaning it doesn't matter what value of m sub L you have. The orbital is at the same energy. So if you want to write same energy, that's perfectly fine. Notice, for same n and L, meaning you have to talk about the same sublevel. So the orbitals within a sublevel all have the same energy, is what that's saying. Any questions? So if we have an L of 0, and we think about our rule, we can only possibly have one value. We technically have negative 0, 0, positive 0, which are all 0. So the only value available is 0. Meaning, since there's one value, there's only one s orbital per energy level. How can the orientation of a ball change? If you turn it, it looks the same, right? But if you turn a peanut around, it can look different. Or turning a daisy around can look different. So it's about the number of numbers you can write. So this is for your table in G. L, where in the first row would be 0. M sub L would be 0. Therefore, the number of orbitals is 1. Because there's one number. The number 0. If we go up to our p orbitals, which is an L of 1 for your second row in that table, well, if we have an L of 1, we have 3 possible m sub L values. We have negative 1, 0, and positive 1. And since there are 3 numbers that we can write, there are 3 p orbitals in a sublevel. That is for p, such as a 2p, or a 3p, or a 4p. Notice none of the numbers is the number 3. It's just about the number of numbers you can write. So for your m sub L values, the second row again, -1, 0, +1, I count 3 numbers, therefore there are 3 orbitals in a sublevel designated for p. If we go up to our d orbitals with an L value of 2, we now have 5 numbers we can write. -2, -1, 0, +1, and +2. 5 numbers that can be written, therefore there are 5 orbitals. And I'd like to use this slide to illustrate which orbital may contain the electron. When you're doing this at higher levels, you start negative here, so this orbital would be designated m sub L value of -2, -1, 0, +1, +2. Only one of those numbers will actually come out of the wave function as a solution. And whichever number that is, that tells you which orbital the electron most likely is in. So that's how it will tell you which orbital contains possibly the electron. For our L value of 3, remember that was with our f orbitals, and we know there's 7 of them because there are 7 possible values for m sub L. If we have an L3, we start at negative L, -3, go through 0, -3, -2, -1, 0, all the way to positive L, +1, +2, +3. 7 numbers can be written, therefore there are 7 orbitals, and each number relates to a specific orbital. -3, -2, -1, 0, +1, +2, +3. Any questions? We have one more quantum number to go through, and the first 3 were the GPS location service, right? The first one told you which energy level. The second one told you which type of orbital within that energy level, so it narrowed down the possible volume in space. The third one told you specifically, not just the type of orbital, which orbital it's most likely in. The fourth one is about the electron's behavior itself. We are on the table slightly close to the bottom of page 234. I think I can squeeze it in underneath here. M sub S. It's about spin. How is the electron behaving? How is it spinning? Rule? The electron can spin in 2 different ways. Not connected to the other quantum numbers. The others are all interconnected. This one is separate. the rule. M sub s either equals positive 1/2 or negative 1/2. How atomic orbitals vary with different values of M sub s? It's independent of the orbital, so it doesn't change the energy of the orbital or the energy of the electron. The energy of electron spinning one way versus one spinning the other way in the same orbital, they be the same energy. How the energy of the atomic orbitals vary with different values of M sub s? They're the same. To illustrate, you can think of the electron being at the low top. You can spin one way versus the other way. We actually use the electron spin analytically to figure out things about molecules. It's called NMR spectroscopy, nuclear magnetic resonance spectroscopy. So just think about, you can put your pen on this counter and you can do one way or you can do the other way. It's just about how the electrons behave. Any questions, Donna? Yes,
What's the half signify? Does it only spin halfway around?
it's the number that comes out of the wave function,
Oh,
plus 1/2 versus minus 1/2.
so it is spinning continuously?
Yeah, oh yeah, it's always spinning.
Yeah, okay.
Well, the positive just tells us one spin, and the negative just tells us the other way. There are actually some subatomic particles that have integer spin, whereas electrons have half integer spin. Is that a question there?
Yeah, one of them different than that.
Okay. You may have learned Pauli's exclusion principle when you did electron configurations, because you can only put 2 electrons in an orbital, right? Well, it all comes down to quantum numbers. No 2 electrons can have the same set of quantum numbers. There's actually 2 meanings behind Pauli's exclusion principle. The fundamental one is about the quantum numbers. No 2 electrons can have the same set of quantum numbers. Therefore, you can only have 2 electrons in any orbital because there's only 2 values of M sub s. The way that we write sets of quantum numbers are always in the same way, and it's already on the screen. N is always first, then L, then M sub s. Sorry, I just messed that up. N is first, then L, then M sub L, and then M sub s. Meaning, if we're in the same orbital, these 3 numbers will be the same. Let's say a 2p orbital. N would be 2, I'll do the other set next to it. And p is what value of L? 1. So I have a 1. To be in the same orbital, we have to have the same M sub L value, so let's just put them both in the center p orbital, 0. This is plus 1/2, the other one is minus 1/2. I cannot put another electron in that orbital, because then I'd be breaking the rules. So that bridges 4 and 5, how we write sets of quantum numbers. Give 2 quantum numbers, sets of quantum numbers that would denote 2 electrons in differently shaped atomic orbitals. These are the same shape. To change it to a different shape, we would change L. So let's put in 0. So this could be a possible answer for number 5. One's in a 2p sublevel, one's in a 2s sublevel. So they're in differently shaped orbitals. The shape changes with the L value. Are there any questions? Yes?
Why do you have 2, 1, 0, negative 1/2 on the right? Just to show.
I was trying to illustrate how you can only have 2 electrons in the same orbital, because 2, 1, 0 is a specific 2p orbital for each.
So then for M sub s, is it always either plus 1/2 or minus 1/2?
Those are the only values allowed, plus or minus 1/2. So there's only 2 values, so you can only put 2 orbitals, sorry, electrons in the same orbitals. I was trying to help you connect to the Pauli's exclusion principle definition you probably learned in the past to this new definition. I did put all of page 235 onto the electricity list, and I know what time it is, don't get up yet. Next time, I'll back up when I start, but we're gonna connect what you have learned in the past, electron configurations, to the quantum number.